Unit 4, Analytical Trigonometry, Solving Trigonomic Equations, Part Deuce 2. That's 2. Part 2. All right, so in the last video, we looked at the basic idea of how to solve trigonomic equations, and we looked at some fairly easy equations that really only involved, kind of one trig function. Maybe you had to do a little bit of solving, but really wasn't too bad. And then we talked about this big idea of, hey, technically all of these trigonomic equations have infinite answers, but, typically we ask for only answers that are in that unit circles, one full rotation from 0 radians all the way around to positive 2 pi radians. So in this video, we're going to talk about a couple medium level problems, and then we'll actually hint into some harder level problems where we need to definitely use some identities. So in these medium level problems, what makes them a little bit tougher is that we're going to have to factor. So oftentimes when we work to solve an equation, factoring comes in handy, right? But we factor to use the zero product property. So remember, what's the point of factoring is we really want to use the zero product property, and we need to have a 0 on one side in order for that to happen. And the zero product property is awesome because when you factor, again, you got to have a 0 on one side, right? But when you factor the other side, when you get something times something, which is of course what factors are, a times b, some value times another value, and the fact that it equals 0, this is a pretty important property that one of those two things has to be 0, because the only way a times b equals 0 is if a or b equals 0. So let's look at a couple algebraic examples of this, and this is going to be like truly old school stuff, but it's important to talk about, right? So let's say we have a problem and it's 3x squared plus 5x equals 0. And we could solve this by factoring. Notice we have an x squared and an x. Those equations usually involve a little bit of squaring, or they involve a little bit more work. You can't just directly solve, because if I try to solve for this x, there's going to be an x squared on the other side. Or if I try to solve for this x squared, there's going to be an x on the other side. So this is where factoring really comes in handy, right? So these are two terms. Terms are anything separated by a plus or minus sign, and both terms have an x in common, so I could factor out that x. And when you factor out, you're essentially dividing it away. So 3x squared divided by x is 3x. 5x divided by x is 5. And I always tell students, if you don't quite believe me that that is the correct factoring, then just distribute that x and you'll see, 3x squared plus 5x. Now here's where the zero product property comes in here, because we have one factor x, and then we have another factor 3x plus 5. And if one of those factors equals 0, then this equation is true. So if x equals 0, 0 times, who cares what this other factor is, you get 0. Or if the 3x plus 5 equals 0, then 0 times any value x is going to be 0. So obviously this one's already kind of solved for us. X equals 0. That's a solution. Doesn't get much easier than that. And this one we're going to do a little bit of work to solve for. We're going to subtract 5. So we get 3x equals negative 5 divided by 3. X equals negative 5/3. Okay, basic factoring problems. Then we could step up our factoring a little bit with trinomials. So maybe a problem like this. I'm sure all of you guys have seen a basic problem like this. Now we could solve this with the quadratic formula. We could solve it by completing the square. But factoring with the, zero product property really makes everything nice and easy and pretty quick. So x breaks down to x squared. 20 breaks down to 5 times 4. But if I want those inside and outside terms to create that negative x in the middle, I need the 5 to be negative, the 4 to be positive. Double check my work, and you do get that. So again, now what I created factors, right? X minus 5, that's a factor, times x plus 4. So one of those factors has to be 0. And that makes the solving really, really simple. So the point, or the reason that I'm taking the time to point all this out is that we're going to use these exact same ideas to solve some trigonomic equations. Now, it might take a hot minute for you to kind of catch on to what I'm doing, but I think you will. All right, so here's one that I kind of already have factored for us, just to show how we could still use the zero product property, even when there's trigonometry involved. So we have a factor. Remember, factors are any two things or more multiplied by each other. So I have a factor, tangent x plus 1, times sine of x minus 5. So if tangent x plus 1 equals 0, then 0 times anything is going to be 0, and I'll get a true statement. Again, this is why you have to have that 0 over here. This just doesn't work. Or sine of x minus 5 has to equal 0, because if this is equal to 0, then 0 times anything is once again 0. All right, so now let's use our trig skills to solve these, because now that I broke this apart to two fairly simple trig equations, they're actually really, really easy to solve. So the first one is tangent x equals negative 1. And then that's something you definitely recognize from the unit circle. Remember, tangent of an angle is the y-coordinate divided by the x-coordinate. So I'm looking for an angle x where the y-coordinate divided by the x-coordinate on the unit circle equals -1. And that should be pretty easy to find. And if you need to pull up a unit circle to look at that, you'll see that at 3 pi over 4, we have a tangent value of -1, and same at 7 pi over 4. So on the unit circle from 0 to 2 pi, our two answers are 3 pi over 4 and 7 pi over 4. All right, but we're not done yet. Now we're going to solve the second equation. So that's pretty easy. Add the 5 over. And now you definitely don't recognize 5 in the unit circle, but two ways you're going to get your answer to this part. First, you could grab your calculator, make sure you're in radian mode, pull the old switcheroo. Now, you're going to instantly get does not exist, can't do, no solution. And that's because there is no solution. Now, if you don't quite understand why the calculator is telling you that, the strategy I told you to anytime you don't recognize the value from the unit circle, the strategy is to draw a quick little picture and say, okay, where is the y-coordinate 5? And that's where you're instantly going to say, oh yeah, that can't happen. Because on the unit circle, the highest the y value is 1. The lowest the y value is -1. The y value will never, ever, ever, ever be 5. It cannot be 5. So that's why there is no solution to sine of x equals 5. So the only solutions to this equation are right there, 3 pi over 4 and 7 pi over 4. All right, let's try another one here. So we have 2 sine squared x minus sine of x minus 1. So the idea here is we're going to factor this much like we factored a trinomial. But again, some kids, it helps if you take the trig out of it for a second. Now, once you get the ball rolling, I don't think you're going to need to do this. But to start, take the trig out of it, right? So let's take the sine of x, and let's just call sine of x w, just for a hot second. So if we do that, then we have 2w squared, because it was sine of x squared, so that'd be w squared, minus w minus 1 equals 0. Now, this is a basic factoring problem, right? This should be very, very quick and painless to factor. So we got 2w times w. I need a 1 and a 1, and in order for there to be a negative w in the middle, I need this to be a -1, this to be a +1. Go ahead and double check my work, but 2w times w is 2w squared. Outside's -2w, inside's +1w. That's going to generate the negative w on the inside, and then 1 times -1 is -1. Now at this point, we could actually go ahead and solve these, right? 2w plus 1 equals 0, or w minus 1 equals 0, using the awesome zero product property. And then again, pretty easy. Subtract the 1 divided by 2. W equals -1/2. Whoa, why the heck did I write a 3 there? Sorry. W equals -1/2. Or add the 1. W equals 1. Now at this point, don't stop. We got to now bring the trig back into the problem. So if I replace the W with sine of x now I can finish solving for the trig portion of the problem. All right, both of these values are some values I recognize right away from the unit circle. So I'm thinking, where is the y-coordinate? What angle x produces a y-coordinate of -1/2? And if I pull up my unit circle, I see that happens at 7 pi over 6 and 11 pi over 6. So we get 7 pi over 6 and 11 pi over 6 to be exact. And the other one here is where is the, again, this is an angle. What angle produces a y value of 1? Well, that's pretty easy, but we'll take a quick look at the unit circle. That's going to happen at the very, very top at pi over 2. So there are my 3, I keep doing that, so sorry, pi over 2. So again, there are my 3 answers to this equation. And again, at first glance, it's kind of tricky, but if you just take the trig out of it for a second, now some kids don't need to do this. They don't need to let sine of x equals w. They just see the factor. They just treat the sine as almost it's its own variable. And that's okay. So that's a good idea, is to treat sine of x like it's a variable until the end, when you then have to solve for the angle that produces that value. All right, let's take a look at another one here. It's another one with cosine this time. And again, if it helps you, just take the trig out of it for a second. So let's have cosine of x equal w. So we have 2w squared minus radical 3 times w equals 0. All right, and this is going to be a 2-term problem. We have 2 terms, 2w squared and radical w. Both terms have a w, so we could factor that out. and we get 2w minus radical 3 equals 0. I just created two factors, so w can equal 0, or 2w minus radical 3 could equal 0. And then I'm going to solve. This one's already solved, w equals 0. And this one I'm going to add the radical 3 divided by 2, so w equals radical 3 divided by 2. And then again, here's what you can't forget to do. Now I got to bring the trig back in. So now I'm going to turn the w back into cosine of x. And I'm going to ask myself, what angle has a x coordinate from the unit circle? That's cosine. What angle has a cosine or an x coordinate of 0? Take a quick look at that unit circle, and that happens at the very, very top. I see the x coordinate of 0, pi over 2, and the very, very bottom, 3 pi over 2. So pi over 2 and 3 pi over 2. All right, then over here, I'm also going to bring the cosine back into the problem by replacing w with cosine of x. And I'm going to ask myself, where do I see an x coordinate? Where is cosine radical 3 over 2? Where do I see an x coordinate of radical 3 over 2? Positive. Again, grab that unit circle. At pi over 6, I see an x coordinate of radical 3 over 2. And then again at 11 pi over 6, I see that happen. So pi over 6 and 11 pi over 6. Now again, I know I don't have written up here. I probably should. We're only looking for answers from 0 to 2 pi. Hopefully you watched in the first video how to address the issue if I'm looking for all answers. All right, so again, factoring really isn't that difficult when you have trigonometry thrown into it. We only looked at a couple of examples here, but don't let it be any more confusing than that. Like, it really is meant to be pretty simple. You're just creating factors with those trig functions. And if you really get kind of nervous, again, I remember when I was doing this back when I was in high school, I got confused by it all. So again, take the trig out of it for a second. Let cosine of x equal w, and then you'll say, oh, that's an easy problem to factor. And then once you're ready, bring the w back in as cosine of x. And then again, we're solving very basic trig functions at that point. All right, now we're going to move into part 3, which is some harder, more difficult problems. And these problems are harder for a couple reasons. I'll do my best to explain. We're only going to look at 3 of them. And I think 3 will be enough, hopefully, to kind of get it through to you guys in terms of how to do these. But the idea here is we're going to have to use the identities. All right, so here's the first one. 2 sine squared of x plus 3 cosine of x minus 3. Now, this is a trinomial, which we just talked about could be done with factoring. But the problem here is that I have a sine of x and a cosine of x. So I can't factor that. Like, let's say I let w equal sine of x. Well, then I'm going to have to let, like, m equal cosine of x. And at that point, I have 2w squared plus 3m minus 3. Well, you can't factor when there's 2 different variables. Like, this just doesn't work that way. You need 1 variable, not 2. So that's just not going to work. So this is why this is definitely a level 3 red flag, very tough problem. Because what I need to do is I need to figure out a way to not have 2 trig functions. I don't want sine squareds and cosine. I don't want cosine and sine. I just want 1 trig function. There's 1 trig function. They're pretty easy to solve, even if I have to factor. So I'm thinking, how could I change one of these, change either the sine squared or change the cosine, so that way I can replace it? Well, that's where the identities come in. And of course, when you see a sine squared, I'm thinking sine squared plus cosine squared equals 1. So here's what I'm going to do. If I subtract the cosine squared over, I get sine squared equals, sorry for my messy handwriting, sine squared equals 1 minus cosine squared. So I could replace the sine squared with 1 minus cosine squared. Now you got to be super careful doing this because that 2 out front is going to need to be distributed. So I have 2. I'm replacing the sine squared with 2 terms, 1 minus cosine squared. So be very careful with that because I'm going to have to distribute that 2. Plus 3 cosine of x minus 3. And voila, just like that, I was able to use an identity to take a function or an equation that had multiple trig functions, which is very hard to solve. And now there's only 1 trig function, cosine. I just have to clean it up a little bit here. So I'm going to distribute my 2. So I get 2 minus 2 cosine squared of x plus 3 cosine of x minus 3 equals 0. Now, something we learned a long time ago when we talked about solving quadratics is they're always easier when the square is positive. So I'm actually going to move everything to the right-hand side because I want this negative 2 cosine squared to be positive. So I'm going to add it over, and I get 2 cosine squared of x. I'm going to subtract the 3 cosine x over, minus 3 cosine x. And then be careful combining like terms here. This 2 and this -3 make a -1, but then I'm going to have to add it over to the other side to get a +1. So I hope everybody followed me on that. Not too difficult there. And if you need to pause and rewind to understand that, pretty simple. But I basically just moved everything to the right-hand side because I'd rather factor with that being squared. And then once again, if you need to come to the side and say, hey, let me let m equal cosine of x, that way I could just see the factoring a little bit easier. So we have 2m squared minus 3m plus 1. And now I have to attempt to factor this bad boy. Let's see if I could do it. So 2m squared could be broken apart by 2m times m. 1 could be broken apart as 1 times 1. And let's see here, if I make them both negative, this is good. So if I make them both negative, on the last term, I get -1 times -1, which is the +1 right here. But on the outside, I get -2m. Inside -1m, that's going to generate the -3m in the middle. So using the zero product property, 2m minus 1 equals 0, which means m equals 1/2. Or m minus 1 equals 0, which means m equals 1. Now I'm going to bring the trig back into the problem. M is cosine of x. So I have cosine of x equals 1/2. Or cosine of x equals 0. And this is going to be just quickly looking at the unit circle. Cosine of x equals 1/2. That's the x coordinate on the unit circle is 1/2. Grab that unit circle. That happens at pi over 3 and 5 pi over 3. So I got pi over 3 and 5 pi over 3. And then I'm going to solve the second one here. Where is an x coordinate 0? So again, look at that unit circle. X coordinate of 0 happens at pi over 2. And 3 pi over 2. So I actually have 4 solutions to this, looking at both of these all together here. All right, awesome. So what a cool problem, right? That's a really, really good problem. And it involves a lot of good math. And right away from the beginning, I had to use an identity to help me out. Let's do that same idea again. All right, so another problem here, secant squared minus tangent squared equals 4. So again, you can't factor, you can't solve when you got two different trig functions like this. It's just not going to work. So that's where I'm going to go ahead and use the identity again. I know that 1 plus tangent squared equals secant squared. So what I'm going to do is I'm going to replace the secant squared right here. I'm going to replace it with 1 plus tangent squared. And this is going to be awesome because now in just real quick there, I was able to have one trig function. All right. There's nothing to distribute, so essentially I have 1 plus tangent squared minus 2 tangent x equals 4. I do need to get everything on one side, though, so I'm going to move everything to the left-hand side there. So I have a tangent squared of x. I have a minus 2 tangent x, and this 4 needs to be subtracted over because I want this to be a 0. So when I subtract that 4 over, it's then going to combine with this 1 right here to get a -3 equals 0. And then again, some kids at this point might not need to, but if you need to, let's go ahead and let w equal tangent of x. So I have w squared minus 2w minus 3 equals 0. That's going to be w and a w. That's how we make a w squared. The factors of 3 are 1 and 3. But let's see here, I need the 3 to be negative and the 1 to be positive. That way I get my -3 at the end. On the outside, I get a -3m. On the inside, I get a positive 1w. Sorry, I said m earlier, w. That generates the -2w in the middle. So w plus 1 equals 0. W minus 3 equals 0. So w equals -1 or w equals +3. All right, so now we're going to bring the trig back in. So, of course, w was tangent of x. So where is tangent of x -1? Take a quick look at that unit circle. Tangent is -1. And again, I'm not going to take the time to explain why. We did that a long time ago. But at 3 pi over 4 and 7 pi over 4, tangent is -1. So again, x equals 3 pi over 4 and 7 pi over 4. Now this one's going to be a little bit tougher to solve. And you'll see why in a second. Tangent of x equals 3. So again, I don't recognize that from the unit circle. Now remember, sine and cosine cannot be bigger or smaller than 1 and -1, but tangent can be anything. So I don't see a tangent value of 3 directly staring at me as one of my well-labeled points on the unit circle, but it's definitely there somewhere. I'm just going to have to use my calculator. So I'm going to pull the old switcheroo to find it. So an inverse tangent of 3 is going to equal my angle. But let's be very, very careful. Remember, you always need to draw pictures here because the calculator might not give you the answer we want, which is why we really need to analyze this with a picture. So where is tangent positive? Tangent is positive somewhere in quadrant 1 and then somewhere in quadrant 3. Tangent repeats itself every half circle. So I can't look in 2 or 4 because that's where tangents are going to be negative. I want to be positive, and it's directly across from each other. So I do go to my calculator. Again, make sure you're in radian mode because we do want our answer in radians from 0 to 2 pi. I am going to have to give decimals here, though, which is no big deal. Do an inverse tangent of 3, and I get 1.25. So that's this angle right here, 1.25. So there's one answer, approximately 1.25. Now, how do I find the other answer? Well, you got a couple options. You could literally just take 1.25 and add pi, add a half circle. Or I can actually do the exact same thing. Remember, if this angle right here is 1.25, so is this angle because of symmetry and geometry. So what I could do is take half a circle, pi, and add that 1.25 to figure out how to get the quadrant 3. So if I take 1.25, add pi, I get 4.39. And again, I'm begging you to check your work, especially on these ones where you do have to go to your calculator. Just type into your calculator tangent of 1.25, and you do get 3.00. There's some decimals there, but again, it's pretty close to 3. It's off because I rounded. And then do tangent of 4.39 as well to confirm that you do get something very, very close to 3. Yes, I should be getting exactly 3, but because we rounded these angles, that's why we're not getting anything exact. And you know what? You can even, it's worth it to check these ones too, right? I mean, just make sure you're in radian mode. Tangent of 3 pi over 4, make sure it says -1. Tangent of 7 pi over 4, make sure it's -1. I mean, you're a fool if you don't check your work. You can always check your work in any equation solving problem. All right, last one here, and this one's definitely a doozy. All right, so we got cosine of x plus 1 equals sine of x. So once again, 2 trig functions. I don't want 2 trig functions. I want 1 trig function. And I love the property sine squared of x plus cosine squared of x equals 1, but I can't use it because these aren't squared. So what the heck do I do? In the previous 2 problems, when I did make the replacement, I had something that was squared that I could make the replacement with. Can't do that here. So think, what can I do? Well, in math, sometimes if we need something to happen, we just make it happen. If I want these to be squared, well, gosh darn it, make them squared. So just go ahead and square both sides. Again, it's rule of algebra. As long as you square both sides, you're going to change how it looks, but you're not actually going to change the problem. So the right-hand side is very easy. It's just going to be sine squared of x, which I love. On the left-hand side, I do have to think, kind of to the side here, what's cosine of x plus 1 times cosine of x plus 1. So let's see here. On the first, I'm going to get cosine squared of x. Outside's a cosine of x. Inside's a cosine of x. I'm going to get a 2 cosine of x in the middle. And then I'm going to get a plus 1 on the outside. So now I'm at a point where I do have squares. And this is good because if I have squares, I can make replacements using this Pythagorean identity. But who do I want to replace? Do I want to replace the cosine squared or the sine squared? Well, I want to replace the sine squared. And the reason is because I still have a regular cosine. And you cannot use the Pythagorean identity on a regular cosine, only a cosine squared. So if I change the cosine to sine squareds, well, then I still have that cosine kind of sitting around there that I can't change. So that's why I'd rather make the change to sine squared, making it 1 minus cosine squared. On the left-hand side, I have cosine squared of x plus 2 cosine of x plus 1. Now I have 1 trig function, and that's cosine. Again, if I would change the cosine squared to 1 minus sine squared, I would still have that cosine of x sitting in the middle with nothing to do about it. All right, so now let me see here. To factor, I need everything on one side, so I'm going to move everything to the left side. So I'm going to add this cosine squared over, and that's going to give me 2 cosine squareds because I'm going to add it to that. I'm going to subtract this 1 over, which is going to give me a 0, which is awesome. So the only thing I have on the left-hand side is 2 cosine squared plus 2 cosine of x. All right, so this is a binomial. There's only 2 terms here. That third term canceled out right there, which is awesome because I could just do the factoring out technique. I'm going to factor out a 2 and a cosine because both terms have a 2 and both terms have a cosine. So when you factor out, you basically divide out. So 2 cosine squared divided by 2 cosine of x is just cosine of x, plus 2 cosine of x divided by 2 cosine of x is just 1. And again, don't believe me, distribute, and you'll see, oh yeah, 2 cosine squared plus 2 cosine. All right, now I'm going to use the zero product property. Either 2 cosine of x equals 0, that's this first factor, or cosine of x plus 1 equals 0, that's the second factor. All right, let's solve each one of these. They're both really easy. Divide by 2, cosine of x equals 0. Where is cosine of x equals 0? Grab that unit circle. How is the very, very top? Pi over 2. Very, very bottom, 3 pi over 2. That's where I have an x coordinate of 0. All right, cosine of x equals -1 after I subtract that 1 over. Where does cosine of x equal -1? That happens at pi. At an angle of pi, I have an x coordinate of -1. If you don't believe me, just take a quick look at that unit circle. And it's actually cut off in my problem here. I'm sorry, the image got cut off. There is a -1 right there at pi. So I actually shouldn't have shown you that. Sorry for that typo there. All right, so hopefully that makes sense to you guys. It's pretty easy. And that there's no questions there, but definitely a tough one here. So again, remember, you can only make replacements if there's squares, because that's what the Pythagorean identities have, squares. And sometimes you just have to force it if you need it to be a square. All right, so those are definitely some hard level problems. But again, so in this video, we looked at factoring and we looked at using the identities. And then typically after we use the identities, we still have to factor. So make sure you know how to factor with trigonometric equations. And it's really not that bad. It makes solving, I think, fairly easy. All right, see you guys in the next video.